Bismillahirrahmanirrahim. Assalamu alaikum. How are you, students? Today our course is Inorganic Material Chemistry and course code is CAM 3115. In this subject we will discuss properties of advanced materials. In your syllabus there are different properties of advanced materials: mechanical properties, electrical properties, optical properties, dielectric, magnetic, and some chemical corrosion properties that you have to study in this course. First we will start from mechanical properties. In this lecture we will discuss mechanical properties and its detail. So today we will discuss about mechanical properties of advanced materials, in which we will discuss Hooke's law, and we will explain the relation of stress and strain. And next we will discuss about Young's modulus and plasticity and plastic deformation of advanced materials that are related to crystals. And then we will discuss hardening, toughness and brittle fracture, and toughening mechanism that are related to advanced materials. And at the end we will discuss applications of mechanically advanced materials in different fields. In previous lecture we have discussed properties of advanced materials, and here our topic is main topic is mechanical properties. Then in this properties we have discussed stress, strain, hardness, strength and elasticity, plasticity, ductility, brittleness, toughness, and malleability. Then we discussed what are advanced materials and what are nanomaterials, and we generally discussed the properties of advanced materials, and then we move toward mechanical properties. So what is Hooke's law? It is related to stress and strain. It is direct relation of stress and strain. So we can say when a material is submitted to an elongation force, its deformation is proportional to that applied stress. So we can say that coefficient of proportionality between the stress, that is sigma, and the strain, that is epsilon, is Young modulus, and it is denoted by sigma is equal to Young modulus, that is denoted by E multiplied by epsilon naught. So Hooke's law जो है वो डायरेक्टली प्रोपोर्शनल है, स्ट्रेस डायरेक्टली प्रोपोर्शनल होता है स्ट्रेन के, और इसको हम अगर कोफिशिएंट ऑफ प्रोपोर्शनैलिटी इसकी जगह यूज़ करें तो उसकी जगह हम यंग मॉडुलस यूज़ करते हैं, जिसको हम ई से डिनोट करते हैं, और यंग मॉडुलस जो है वो है स्ट्रेस डिवाइडेड बाय स्ट्रेन. Young's modulus is stress over strain, and it is denoted by Young's modulus is denoted by E. So we already discussed about strain, that it is change in the length of that material divided by its original length, and stress is force divided by cross sectional area. So we can represent stress as F over A and strain delta L over L, and it is known as the stress over strain divided by strain is Young's modulus, and if stress and strain are directly proportional, then that is known as Hooke's law. So what is plasticity? Plasticity is non-reversible deformation in response to an applied stress or force. So plastic deformation of single crystals, how it happens? When a material plastically deforms, actually what happens, its surface exhibits, it shows surface of that material shows slip bands, and these slip bands are the emergence on the surface of dislocations. These slip bands are due to the emergence of dislocation on that surface, and the orientation of these bands depend on the that crystallographic structure of material in which that plastic deformation of crystals occur. So here you can see in the figure, you can see that slip direction is on the right side, and the slip, you can see here slip planes and steps that are known as slip steps, and the bands, here you can see bands in blue color, dark blue color, these are known as slip bands. So when dislocation occurs, these plastic deformation may take place in that single crystals, and this depends upon the how the crystals crystallites are arranged in that material and what is orientation of that bands. So when they slip, there will be plastic deformation in that material, and that plastic deformation is non-reversible deformation. It cannot return to its original shape. So dislocations are actually another type of defect that is present in crystals. And dislocations are areas, are the regions where that atoms are out of position in crystal structures. When atoms are out of position in any crystal structure, then we say that are called dislocations. And dislocation is actually defect in crystal. Are dislocations are generated and move when a stress is applied. So when dislocations actually occurs when you apply any force or stress, then these dislocations may occur and they can move. So the motion of that motion of dislocation allows slip plastic deformation to occur. As in previous example, we see that due to dislocations, that emergence of that uh, defects in crystals may occur, and the slip bands starts in that material, due to which that materials will be deformed. If we compare early measurements that are performed on nanostructure materials, and then these are compared with the conventional grain size materials like bulk materials or micro materials, then these experiments showed that the nanostructure materials has lower Young's modulus value as compared to conventional or bulk materials. So mostly the nanomaterials have less defects, they have less dislocations. Before we discussed, generally we discussed about hardening and hardness of materials. So hardness of materials occur when the motion of dislocations become difficult, even impossible in that material. So that material will be hard in which motion of dislocation is difficult. So that materials will show hardening properties, or they will show hardness. So plastic deformation starts when dislocation scales become very active under the applied stress. So जब आपके पास जो है वो जो मटेरियल है उसमें डिसलोकेशंस अगर फॉर एग्जांपल उसमें डिसलोकेशंस हैं ही नहीं, तो उसमें जो डिफेक्ट्स वगैरह नहीं है, तो उसमें जो मोशन होती है, उसमें जब स्ट्रेस अप्लाई करते हैं तो उसमें डिसलोकेशंस को मूव करने की, जो स्लिप होने की बैंड्स की एबिलिटी कम होती है, जिसकी वजह से वो मटेरियल हार्ड होता है, उसकी प्रॉपर्टी हार्डनेस प्रॉपर्टी वो शो करता है। और प्लास्टिक डिफॉर्मेशन किस केस में होती है? जब आपकी प्लास्टिक डिफॉर्मेशन तब होती है जब आपकी डिसलोकेशन स्केल जो है, डिसलोकेशन बहुत ज़्यादा होती हैं, और डिसलोकेशन जब होती है तो उसमें स्ट्रेस जब अप्लाई करते हैं तो उसमें मोशन भी ज़्यादा होती है, और जब कोई चीज़ जो है अपनी उससे मूव कर जाएगी और दोबारा उसमें वापस नहीं आ सकेगी, तो फिर आप कहते हैं कि उसमें प्लास्टिक डिफॉर्मेशन हो गई है, तो उसमें प्लास्टिसिटी की जो है इलास्टिसिटी कम है और उसमें प्लास्टिसिटी की property है. So what is hardening process? When we want to increase the property of that material, or we want to make it harder. For example, atoms in solid solutions create elastic distortions. They can create elastic spin, or they can create elastic alteration and stress field around them. So the interaction between these dislocations and stress may lead to higher hardness. अगर आप कोई मटेरियल को उसमें ज़्यादा हार्डर बनाना चाह रहे हैं तो उसमें आप एटम्स को जो है इस पोजीशन में करेंगे कि उसमें प्लास्टिक डिफॉर्मेशन ना हो, उसमें इलास्टिसिटी हो, और जब आप अप्लाई करें उस पर जब स्ट्रेस अप्लाई करें तो उसमें जो है वो उसकी हार्डनिंग प्रॉपर्टीज़ मेंटेन रहें. सो इन दोनों के इंटरेक्शन जो है डिसलोकेशंस और जो स्ट्रेस है इन दोनों को इस तरह मेंटेन किया जाता है कि उसमें जो है डिफॉर्मेशन ना हो और उसकी हार्डनिंग जो है प्रॉपर्टीज मेंटेन रहे. In case of hardening process, among many of the novel mechanical properties of nanostructure materials, high hardness has been discovered from many nanostructure materials. So in few appropriately sized systems, the hardness of nanomaterials or nanocomposites exceeds significantly than that of mixture in bulk. So super hardness also comes from pure nanoparticles. आप जो है कोई भी मटेरियल है, फॉर एग्जांपल सिंगल उसमें यूज़ कर रहे हैं तो दो मटेरियल्स को उसका कंपोजिट बना के, उसको नैनो कंपोजिट बना के उसकी प्रॉपर्टीज़ को फर्दर इन्हांस कर सकते हैं. तो एक बल्क मटेरियल अगर आप लेते हैं उसमें डिफरेंट मिक्सचर आपने यूज़ किया, उसकी बजाय अगर आप उसमें नैनो कंपोजिट यूज़ करते हैं जिसमें नैनो पार्टिकल्स और आपने साथ जो है कोई दूसरा मटेरियल यूज़ किया जिसमें वो प्रॉपर्टीज़ दोनों की जो है वो कंबाइन हो जाएंगी और आपके पास जो है वो फॉर एग्जांपल सुपर हार्डनेस की अगर हम एग्जांपल देते हैं तो वो आपको प्योर नैनो पार्टिकल्स में जो है अगर उसमें कंपोजिट्स के साथ आप प्योर नैनो पार्टिकल्स और कोई दूसरा मटेरियल उसको कंबाइन करते हैं तो आपके पास सुपर हार्डनेस आती है. For example, super hardness from nearly spherical defect-free silicone nanospheres, whose diameter is from 20 to 50 nanometer, are they have about 4 times greater than bulk silicone, have hardness more than that of bulk silicone. Even if you apply the pressure of or force of 50 gigapascal. Still it is greater than, it's harder than bulk silicone. So सुपर हार्डनेस हमने जैसे बात की कि सुपर हार्डनेस जो है वो नैनो पार्टिकल्स जो है अगर आप उसको कंबाइन करते हैं किसी उसके साथ तो उसकी वजह से उसकी सुपर हार्डनेस या उसकी हार्डनेस बहुत ज़्यादा हो जाती है, एक्सीड कर जाती है बल्क मटेरियल से. तो एक्चुअली जो नैनो पार्टिकल्स हैं उसमें डिफेक्ट्स कम होते हैं. डिसलोकेशन जो हम उसको इस तरह प्रिपेयर करते हैं कि डिसलोकेशंस कम हो, हम उसको नैनो स्केल पे जो है उसको देख सकते हैं ग्रेन साइज को. तो सुपर हार्डनेस जो है जैसे हम स्फेरिकल डिफेक्ट फ्री सिलिकॉन नैनोस्फीयर्स के एग्जांपल देते हैं जिसका डायमीटर 20 to 50 नैनोमीटर है. ये सिंथेसाइज किए गए हैं और अप टू 50 गीगापास्कल प्रेशर को जो है या स्ट्रेस को ये तक अपनी प्रॉपर्टी हार्डनेस को मेंटेन कर सकते हैं जो कि 4 times ग्रेटर है दैन दैट ऑफ बल्क सिलिकॉन. Toughness, ability of material to absorb energy during deformation up to fracture is known as toughness. So a material is generally considered tough if it withstands high level of stress and can dissipate strain energy without brittle fracture. So and then we will talk about brittleness or brittle fracture. And when we are checking mechanical properties of any material for designing, so instead of that strength and hardness, toughness is also very important, and we should know the this property as well in addition to strength and hardness. So what is brittle fracture? Brittle fracture is the result of rapid crack growth. So as the failure mechanism of high strength materials like nanomaterial is governed by brittle fracture. So the toughness is the key mechanical property that is used in mechanical designing instead of strength and hardness alone. So toughening mechanism, what we can do for making materials tough. So for that purpose, multi-layering is an important mechanism, and we can one way to improve nanomaterial toughness is to combine a hard nanocrystalline phase with a soft metal matrix. This is one way in which we can combine hard nanocrystalline phase with a soft metal matrix, and we can improve its toughness. And toughening can be done using multi-layer design. We can prepare multi-layers of that material and we can make it tough. And number and thickness of layers are combined to get the resulted toughness. So we can add different layers, multi-layers, which can increase the toughness of that materials. In below figure, you can see that this gray color is for ductile layer, and this is ductile layer, and the white layer is for brittle material. So we can combine these two, ductile and brittle material, and we can get tough material with toughening properties. As we discussed about mechanical properties of materials, advanced materials, and their characteristics related to their structures. So if we consider these unique mechanical properties, then nanoparticles can be used in a variety of these advanced materials can be used in different applications in different fields. So here we will discuss some important applications. So first is tougher and harder cutting tools can be can be designed by nanomaterials. So cutting tools that are made up of nanomaterials include tungsten carbide, and you can say titanium carbide. These are two examples of cutting tools that are made up of nanomaterials, and these both are much harder, and they have much more wear resistance. What is wear resistance? What is meant by wear resistance? It is a loss of material from a surface by means of some mechanical action. If you apply some mechanical force, or you apply some force and there is a loss of material, then we say that this material is up to which force this material can maintain its uh, shape or can maintain its surface. And these cutting tools are erosion resistant. They cannot be affected easily by oxidation or rusting, and these may last longer than their conventional counterparts. If we are talking about the nanomaterials cutting tools, that examples are tungsten carbide and titanium carbide. They are much harder and they are much wear resistant and they are erosion resistant, and they may last longer than their conventional counterparts. It means they are more stronger and they have much better properties than the bulk materials or micro materials. So as we take the example of nanocrystalline carbides, as they are much stronger and harder and wear resistant, so they are being used in micro drills in industry. Here is the figure of this micro drills. Below you can see, and these are made up of nanocrystalline carbides, and which may be tungsten carbide or which may be titanium carbide. Next application for mechanical properties is automobiles with great field efficiency are used As nanomaterials are stronger, they are harder and much more wear resistant, and these are erosion resistant. Then they can be used in spark plugs. A water spark plug. Spark plug is a device for firing the explosive mixture in an internal combustion engine. Here is a figure for spark plugs. So in automobiles mostly waste a large amount of energy by losing the thermal energy that is generated by engine. So engine cylinders are planned to be coated with nanocrystalline ceramics such as zirconia and aluminium, and which retain heat much more efficiently, and they results in complete and efficient combustion of fuels. So mostly automobiles waste energy in the form of thermal energy in the form of heat. So engine cylinders that are coated with nanocrystalline ceramics, examples of these nanocrystalline ceramics are zirconia and alumina. These cylinders are coated with that materials which retain that heat more efficiently, and they reduce the loss of that thermal energy, and make the engines are more efficient, and make the combustion of fuels less. So next application is aerospace components with enhanced performance characteristics. Fatigue strength increases with a reduction in grain size of material. Now we can say that nanomaterials provide a significant reduction in grain size over conventional material, due to which the fatigue life is increased by an average of 200 to 300%. So, what is actually fatigue? Fatigue life or fatigue. So, fatigue is a weakening of material that is caused by cyclic loading or stress that results in progressive and localized structural damage and the growth of cracks. फटीग क्या है कि जब भी किसी मटेरियल पे आप साइक्लिक जो है वो रिपीटेड वे में जो है, और जब आप डिफरेंट साइकिल के साथ उस पर स्ट्रेस बार बार अप्लाई करते हैं या उस पर लोड अप्लाई करते हैं, तो वो उसकी वजह से क्या होता है कि एक जहाँ पे स्ट्रेस अप्लाई हो रहा है बार बार, वहाँ पे स्ट्रक्चरल डैमेज हो जाता है या क्रैक जो है वो बढ़ना शुरू हो जाता है. So what is fatigue like? The number of loading or stress cycles of a specified character that a specimen sustains before failure of that specified natures occur. इन फटीग लाइफ क्या होगी कि आप जब उसको अप्लाई करते हैं, नंबर ऑफ लोडिंग साइकिल्स जो है उस स्पेसिफाइड मटेरियल पे अप्लाई करते जाते हैं, तो वो उसकी फटीग लाइफ डिपेंड करता है कि वो कितने स्ट्रेस को जो है वो बियर कर सकती है, कितने साइकिल्स तक जो है उसमें डैमेज या क्रैक नहीं पड़ता, तो उसको हम फटीग लाइफ कहते हैं. So in spacecrafts, elevated temperature strength of material is important because the components such as rocket engines and vectoring nozzles operate at much higher temperature than aircrafts and the higher speeds. So these nanomaterials can provide fatigue strength and greater fatigue life as the size of material is decreased. Next are ductile ceramics. Ceramics in bulk, if we consider them, they are very hard, brittle, and these are difficult to design even at higher temperature. But with a reduction in grain size, their properties change drastically. If we compare nano size ceramics with bulk materials, we say that ceramics are very hard and brittle, and it is difficult to design them at very high temperatures. But if size is increased in nanometer range, then their properties are completely changed. So nanocrystalline ceramics can be pressed and sintered into various shapes at significantly lower temperature. When these are converted into nanocrystalline ceramics, then they can be pressed and they can be shaped into various form, or they can be calcined or sinters at very low temperatures instead of high temperature. For example, zirconia is a hard and brittle ceramic and has even been rendered as superplastic. It can deform to great lengths up to 3 times of its original length. And however, these ceramics must possess nanocrystalline grains to be superplastic. So, ceramic that are based on silicon nitride and silicon carbide have been used in automotive applications as high-strength springs, ball bearings, and valve filters, and because they possess good formability and these have a good mechanability, so these combined with excellent physical, chemical, and mechanical properties, and they have a we can prepare different materials from them, and they are also used as components in high temperature furnaces. So we can shape these silicon nitrides and silicon carbides for different automotive applications. We can form their components and because they have a good, we can convert them into different shapes, and they have a good physical, chemical, and mechanical properties. So they could be used as a components in high temperature furnaces, as they can withstand high temperature as well. Assignments that you have to search after reading all these, or you can also search out these references I have mentioned here, and you can thoroughly study these mechanical properties, and you have to find the nanomaterials or advanced materials that are mechanically strong and that have been synthesized and being used in our daily life. You can take any example of any material and any daily life example of that material in which these are mechanically strong and which are made up of that nanomaterials.